Module 5, Section 9.4, the inverse circular functions. First, let's look at a review of inverse functions from algebra. If a function is one-to-one, then f has an inverse function called f inverse, indicated with the -1 in the exponent. In a one-to-one function, each x value corresponds to only one y value, and each y value corresponds to only one x value. The domain of f is the range of f inverse, and the range of f is the domain of f inverse. The graphs of f and f inverse are reflections of each other about the line y equal x. To find f inverse of x from f of x, we follow these steps. First, we replace f of x with y and interchange x and y. Step 2, we solve for y, and step 3, we replace y with f inverse of x. This is just a review of what we do with algebra to find inverse functions. Let's look at the inverse sine function first. We can apply the horizontal line test to show that y equals sine of x is not one-to-one. However, by restricting the domain over the interval -pi/2 to pi/2, a one-to-one function can be defined, as you can see in the picture below. With the inverse sine function, we have that y equals sine to the -1, read sine inverse of x, or y equals arc sine of x. This means that x equals the sine of y, for y being values between -pi/2 and +pi/2. So notice that sine inverse of x and arc sine of x are both ways to say our inverse sine function. The domain of the inverse sine function, y equals sine inverse of x, is -1 to 1, while the restricted domain of y equals sine of x, which was -pi/2 to pi/2, is the range of y equals sine inverse of x. We may think of y equals sine inverse of x as y is the number in the interval -pi/2 to pi/2, whose sine is x. And here we see a graph of our sine inverse function with various points plotted. Here we have our unit circle and our sine inverse function graphed side by side so that we can compare. Notice the points. Let's compare this one. At pi/6, we have the point √3/2 and 1/2 on our unit circle. With the sine inverse function, remember that we flip x and y, so now our y value from before is our x value here, and our angle pi/6 is our y value. And you can notice that with each point that's plotted if you compare it with the points on the unit circle. Now let's find inverse sine values. We want to find y in each equation. First, we want to find y equal the arc sine of 1/2. Remember, when we have y equals our sine inverse or arc sine of x, that means that x is equal to the sine of y. So here we have that x is equal to 1/2. So then we have that 1/2 is equal to the sine of y. So we're trying to find the value of y that when we take the sine of it will give us 1/2. So we need to know the angle in this case. Let's look at our graph first, and then we'll show another method to find it. On our graph, we see that when we have an x value of 1/2, that our y value was pi/6. So we get a value for y of pi/6, or 30 degrees. Now let's do part B. We see that we have an x value of -1, so we say that -1 is equal to the sine of y. So we want to find the y value or angle. When we take the sine of it, that will give us -1. We look at our graph and we see that -1 is down here. Our x value, -1, gives us a y value of -pi/2. So we have that y is equal to -pi/2. Now let's look at part C. Y equals the sine inverse of -2. In this case, x is equal to -2, So we want to find the value for y that says the negative 2 is equal to the sine of y. But notice that negative 2 is not in the domain. The domain of our sine inverse function was negative 1 to 1. Which was the range of our sine function. So since our x value is not in the domain, then we have that the sine inverse of negative 2 does not exist. So now let's look at another method to find these. Instead of looking at the graph, we'll look at our calculator. Now let's make sure we're in degree mode, as we are here. When we clear out, we'll take the sine inverse of y, so we press second and sine to give us sine inverse, and we type in our 1/2. We see we get a value of 30 degrees, and we can convert that to radians if you like, simply by dividing it by 180 and pressing math, enter. We see we get 1/6, and we simply add pi to the top to get pi over 6. That's a way to find our radian measures on our calculator if you like. Now let's do part B. We do second sine of negative 1, and we see we get negative 90 degrees, which when we convert, we divide by 180 and change it to a fraction. We get negative 1/2, and we add pi to the top, so we get negative pi over 2. Now let's look at what happens when we try to do part C on our calculator, and remember that we saw already that it does not exist. So I press second sine of negative 2 and hit enter. And here we get our error function. When we have a go to option, we'll arrow down to it and hit enter. And notice that it's telling us that it doesn't understand our input for our sine inverse function. So when you get this error, I'll hit enter again, we know the error is in the domain, that our value is not in our domain, so sine inverse of negative 2 does not exist. One caution, in part B it is tempting to give the value of sine inverse of negative 1 as 3 pi over 2. However, 3 pi over 2 is not in the range of the inverse sine function, so you have to make sure that we use our negative pi over 2 instead. Here we have a breakdown of our inverse sine function with the domain and the range and the graphs. You see the graph here and the graph on our calculator with a list of the table values. We also see some properties. The inverse sine function is increasing and continuous on its domain of negative 1 and 1. Its x-intercept is 0 and its y-intercept is 0, as we see right here. Its graph is symmetric with respect to the origin. Now let's look at the inverse cosine function. The function y equal cosine inverse of x, or y equal arc cosine of x, is defined by restricting the domain of y equal cosine of x to the interval 0 to pi and reversing the roles of x and y. Here we see a graph of our arc cosine or cosine inverse function. So our definition, y equal cosine inverse of x, or y equal arc cosine of x, means that x equals the cosine of y for y being between values 0 and pi. Here we see our unit circle and our arc cosine graphs side by side, so that you can again compare how the points line up as we did with our arc sine function. Now let's find inverse cosine values. We want to find y in each equation. And remember, when you have y equals the arc cosine or cosine inverse of x, that also states that x is equal to the cosine of y. So in this case, x is equal to 1. So we have that 1 is equal to the cosine of y So we want to find the y value such that when we take the cosine of it, we'll get 1. So we look here when x is 1, and we see that we get a y value of 0. Now let's also look at part B. We want to take the cosine inverse of negative square root of 2 over 2. So we have that x is negative square root of 2 over 2, and we say that negative square root of 2 over 2 is equal to the cosine of y. So we want to find our y value so that when we take the cosine of it, we get negative square root of 2 over 2. So let's find our x value, negative square root of 2 over 2, and we see that it's over here. And our y value then is 3 pi over 4. So now let's look at finding these on our calculator. We want to take the arc cosine or the cosine inverse of 1, so we press second cosine inverse of 1. Again, make sure you're in degree mode. And you see we get 0. And now let's take the arc cosine of negative square root of 2 over 2. And you see we get 135 degrees, which when we convert it to radians, we divide by 180 and change it to a fraction, and then simply add pi to our numerator, and we get 3 pi over 4. So here we have a breakdown of our inverse cosine function with our domain and our range listed, and the graphs on the screen and on our calculator, also with the table of values listed. We see that the inverse cosine function is decreasing and continuous on its domain of negative 1 to 1. Its x-intercept is 1 and its y-intercept is pi over 2. Its graph is not symmetric with respect to the y-axis nor the origin. Now let's look at our inverse tangent function. The function y equal tangent inverse of x, or y equal arctangent of x, is defined by restricting the domain of y equal tangent of x to the interval negative pi over 2 and pi over 2, and reversing the roles of x and y. Here we see our graph of our original tangent function, and we're restricting from negative pi over 2 to pi over 2, which was just one period of our original tangent function. And when we reverse the roles, now we see our points plotted, and we have our arctangent or tangent inverse function. So, y equal the tangent inverse of x, or arctangent of x, means that x equals the tangent of y for y values between negative pi over 2 and positive pi over 2. And here we see a breakdown of our inverse tangent function. Notice that the domain is negative infinity to positive infinity, and the range is our restricted domain from our tangent function. We see our graphs here, and notice the inverse tangent function is increasing and continuous on its domain. Its x-intercept is 0 and y-intercept is 0. Its graph is symmetric with respect to the origin and has horizontal asymptotes y equal plus or minus pi over 2, which were originally our vertical asymptotes in the tangent function. Here we see a table breaking down the remaining inverse trigonometric functions. So we've already looked at sine, cosine, and tangent inverse, and now we see cotangent, secant, and cosecant written out for us with our domain, the interval that it's restricted on, and the quadrants that it will be graphed in. Our inverse trigonometric functions are formally defined with real number values. Sometimes we want the degree measured angles equivalent to these real number values. Let's do some examples. We want to find the degree measure of theta in each of the following. So in this case we have that x is equal to 1, so we have that 1 is equal to the tangent of theta. We want to find the value of theta that when we take the tangent of it, we get 1. With our arctangent function, we know that theta must be in the interval negative pi over 2 to pi over 2, or negative 90 degrees to 90 degrees. but since 1 is greater than 0, we know that theta is in quadrant 1. So the tangent of theta that will give us 1 is 45 degrees. We can also do our inverse tangent function of 1, and we get 45 degrees. Now let's do the secant inverse of 2. So we say that x is equal to 2, and we know then that 2 is equal to the secant of theta. So we want to find theta such that when we take the secant of it, we get 2. For secant inverse of x, theta is in quadrant 1 or 2. Since we know that 2 is greater than 0, then we know that theta is in quadrant 1. Now to find this secant we can't do on our calculator, so we want to convert to cosine, its reciprocal function. So we know that the secant inverse of 2 is equivalent to the cosine inverse of the reciprocal, or 1/2. So let's look at our calculator. So we take the cosine inverse of 1/2, and we see that we get 60 degrees for theta. Let's look at some more examples on our calculator. We want to find y in radians if y is equal to the cosecant inverse of -3. So we have y equals cosecant inverse of -3 is equivalent to the sine inverse of -1/3. So we want to find on our calculator that value in radians. So let's change our mode to radian mode. We hit enter and clear. And now we'll do the sine inverse of -1/3. And we see we get a value of -0.3398. In this next example, we want to find theta in degrees if theta is equal to the arc cotangent of -0.3541. So we know that the arc cotangent of our value is equivalent to the arc tangent of 1 over our value. Take note that a calculator will give the inverse tangent function of a negative number as a quadrant 4 angle, but the restriction on the range of arc cotangent means that theta must be in quadrant 2, so we have to add 180 degrees here when we take the arc tangent of our reciprocal. So let's look at our calculator. We want to switch to degrees. And we'll take the arc tangent or tangent inverse of our reciprocal and we get a value of -70.5, but we'll want to add 180 as our restriction states to get 109.499. degrees. This is going to be important when you're dealing with cotangent and tangent inverse functions when you switch between the two. In this example, we want to evaluate each expression without a calculator. First, we want to find the sine of the tangent inverse of 3/2. So we're going to let theta be equal to the tangent inverse of 3/2. So that means that when we replace that with theta, we're trying to find the sine of theta. But we can rewrite this as the tangent of theta is equal to 3 over 2. And remember that tangent is defined as y over x. So let's look at a triangle. In quadrant 1, we have a right triangle, and we put our y value as 3, and our x value is 2, and we use the Pythagorean theorem, a squared plus b squared equals c squared, to evaluate and get our hypotenuse of square root of 13. Remember that sine is defined as y over r, or the opposite over the hypotenuse. So we have 3 over the square root of 13, and when we rationalize that, we'll get a value of 3 square root of 13 over 13. Now in part B, we want to take the tangent of the cosine inverse of negative 5 over 13. So let's split this up here. We're going to let A be equal to the cosine inverse of negative 5 over 13. So that means that the cosine of A is equal to negative 5/13, which is x over r. And we're trying to then find the tangent of A. So we set up a triangle similar, and we see that when x is negative, we're in quadrant 2 with our cosine, and we have the adjacent over the hypotenuse, or x over r. We use our Pythagorean theorem to find our last side, which will be 12, and we remember that tangent function is y over x, or the adjacent over the opposite over the adjacent. So we have 12 over negative 5, or just negative 12/5 for our tangent function here. In this example, we want to write each expression as an algebraic expression in u. So we will let, in part A, theta be equal to the tangent inverse of u, and that means that the tangent of theta is equal to u, and we remember if we make it a fraction that tangent was our y over our x, and tangent inverse, remember, is in quadrants 1 and 4. So we set up a triangle in quadrants 1 and 4, since we don't know what tangent is, if it's positive or negative, since we're given a variable here. And we're trying to find the sine then of theta, which will be y over r. So we set up our y value will be our u here, and our x value is 1. Notice that in quadrant 1, u is positive, and in quadrant 4, u is negative. When we do the Pythagorean theorem to find our hypotenuse here, we'll get the square root of u squared plus 1. So we find that the sine of theta will be equal to our y value, which is u, over our r, or hypotenuse, which is the square root of u squared plus 1. This value will be positive when u is greater than 0, and it'll be negative when u is less than 0. In this next example, we want to find the cosine of 2 sine inverse of u. So I'm going to let theta be equal to simply the sine inverse of u, so then we'll have the cosine of 2 theta, which means we'll need to use one of our double number identities. So this first part means that u is equal to the sine of theta. And we'll use our double number identity that involves only sine. So we have 1 minus 2 sine squared of theta. And we'll plug in our value for sine of theta, which we have as u. So we have 1 minus 2u squared, or a value for our function of 1 minus 2u quantity squared. Now let's find function values using identities. We want to evaluate the following expression without using a calculator. We want to take the cosine of the arctangent of square root of 3 plus the arcsine of 1/3. So this would be our sum identity. And remember, when we have the cosine of a plus b, that is equal to the cosine of a times the cosine of b minus the sine of a times the sine of b. So we know in this case that a is equal to the arctangent of square root of 3. That means then that tangent of a is equal to the square root of 3, which will make square root of 3 over 1 to get y over x for a tangent. And we have that b is equal to the arcsine of 1/3. So the sine of b is equal to 1/3, which is y over r. Now the arctangent is positive in quadrant 1 and the arcsine is positive in quadrant 1. So let's set up triangles in quadrant 1. For a, we see that the tangent of a was square root of 3 over 1, so we have y over x would be square root of 3 over 1 here. And when we do the Pythagorean theorem, we'll get a value here for our hypotenuse of 2. And then let's set up b. We have that the arcsine, or sine of b, equals 1/3. So we have 1 as our y value and 3 as our r, or hypotenuse. When we do the Pythagorean theorem here, we'll get a value of 2 square root of 2 for our x value. So we need the cosine of a, which will be 1/2. We need the cosine of b, which will be 2 square root of 2 over 3. We need the sine of a, which is equal to the square root of 3 over 2. And we need the sine of b, which we already know to be 1/3. So we'll plug those in, and we'll get 1/2 times 2 square root of 2 over 3 minus square root of 3 over 2 times 1/3. Remember, we're plugging into this equation here. So we evaluate and we can eliminate our 2's here, and we get the square root of 2 over 3 minus the square root of 3 over 6. So this, when we multiply, we'll get 2 square root of 2 over 6. So that we can put them together, we have 2 square root of 2 minus the square root of 3 all over 6. Now let's look at an application. We want to find the optimal angle of elevation of a shot put. In this example, the optimal angle of elevation, theta, a shot putter should aim for to throw the greatest distance depends on the velocity of the throw and the initial height of the shot. One model for theta that achieves this goal is given in this equation here. Suppose a shot putter can consistently throw a steel ball with height h equals 7.6 feet and v, the velocity, equal to 42 feet per second. At what angle should he throw the ball to maximize the distance? So what we want to do is use the equation we were given before and plug in the values for v and h. So we have that theta will then be the arcsine of the square root of 42 squared over 2 times 42 squared plus 64 times 7.6. So we want to plug this into our calculator. Now first I'll evaluate my square root here. So let's do the fraction inside. We have 42 squared is divided by the denominator, which is 2 times 42 squared plus 64 times 7.6. Then we want to take the square root of that answer, so we do our square root symbol and then do second and our negative key to type answer, so we don't have to retype the decimal. And now I want to take the arcsine of that, so we'll do second sine inverse of our answer here. and we see that we get a value of theta, and remember our mode was degree, so we see that theta is approximately 41.5 degrees, and that will be the optimal angle that he needs to throw the ball.